Okay, so we're starting Unit 2. Unit 2 consists of two things. The first half of Unit 2 is business statistics. We take all of 2 weeks on statistics. I could easily fill up 2 semesters on statistics if I wanted to, so I will pull myself back as much as I can. To me, I think statistics, for anybody going into business, it's a very important thing to do because that's how you understand information and it's how you make informed decisions. So what we're going to do in our two nights worth or 2 weeks worth is just a very, very light skim of the surface of statistics. And then the second part of it is merchandising. Merchandising is just, yes? So merchandising is basically getting the material, the objects, the products from the manufacturer to a distributor or wholesaler and then to the retailer. And we'll break that down into 2 parts, the manufacturer distributor and distributor to retailer. And again, we'll talk about that starting in a couple weeks. So for tonight, we're starting with the business statistics. When we talk about statistics, what statistics is just the gathering and analyzing of data. So it brings to the question of what is data? Well, data is nothing more than information about a topic or a question. The key to statistics is asking a question. And you have to ask a question in such a way that you can actually gather information about it. I mean, you can't ask, something like, what's the secret to life or something like that. You're not going to be able to gather a whole lot of information about that. But if you ask, what is the average amount that a homeowner's or a household spends on clothes in a year or something like that, you can gather information on that. And that question that we ask can be broken down into a couple of different categories. It can either be qualitative or often called categorical, depending on which book you're looking. Or it can be quantitative. Or sometimes called numerical. And again, it's basically what is the answer to this question that's being asked. Does the answer to the question put you in a category? Then it is qualitative or categorical. What's your favorite color? If you say red, well, that puts you in the category of people that choose red. Are you going to vote? How are you going to vote on this topic? Yes or no? It puts you in any question that's yes or no is categorical. It puts you in a yes or no category. Quantitative, well, then the answer to that question is a number. And it can be broken down into 2 types. It can either be discrete. Discrete answers or discrete variables are counted. Like how many cars do you own? How many kids do you have? 1, 0, 1, 2, 3, so on. Or continuous. Continuous is something that is measured. Like how tall are you? How much do you weigh? These are things that are measured, and it's called continuous because no matter how close together 2 links are or two answers are, it's always possible to get an answer that's in between them. So it's a continual series of numbers, continuous graduation. So anyway, we can break our data down into these categories. Once we've picked our question, we've formulated our question, though, we have to somehow gather the data. And to gather that data, we have to look at what is it that is our population of interest. The population is the group that we want to learn about. For example, if we want to know who's going to win the next presidential election, the group that we want to learn about is not the presidential candidates. The group that we want to learn about are all people who are going to vote in that next election. We want to learn about what their behavior is going to be and try to predict that behavior. So it's sometimes a little tricky to define that population. If I want to know what's the average amount that WITC students spend on books in a semester, the group we want to learn about is all WITC students. In many cases, we cannot look at the entire population. The entire population is just too big, so we choose a sample. Several reasons why we would choose a sample. A sample is just a smaller group from the population. Many reasons why we would choose a sample rather than looking at the whole population. One reason, time. If I wanted to try to find out, who's going to win the next presidential election, if I wanted to try to call everybody who's going to vote in the next election and see who they're going to vote for, it would take me. In fact, the election would probably be over and would probably be almost to the next presidential election. There just isn't time. 2, this one's a little vaguer. I should have put money up here first, but can't define. We don't necessarily know who's going to vote in the next presidential election. You might call somebody up. They might not know yet if they're going to vote in the next election. So you can't necessarily define the whole population, so you have to choose a sample. Then, of course, money. It costs, every person you survey or sample is going to cost you some money. You can't afford to do everybody. You save some money by only doing a few. This next one is one that's kind of, again, a little bit vague. Changes in conditions, or just changes is how I'm going to label it. Let's say it's going to take, you want to survey a really large group of people on the election. And it's going to take you like 6 months to do the survey. Well, during that time, the candidates aren't just sitting back doing nothing, waiting for you to finish your survey. They're campaigning, they're bringing up points and policies and getting caught in scandals or whatever. The first person you surveyed may change who they're voting for by the time you get to the last person you're going to survey. So you need to do it quickly in order to avoid those changes. It's important that a survey or a sample be a snapshot of what's going on right now, and we have to make sure it's done quickly enough that you don't have those. Then the last one we're going to list, there's a lot of other ones, but destructive. This isn't necessarily so in surveying voters, but in industry. We use statistics and quality control. And let's say we have a specification that a part that we're going to build needs to be able to hold a certain amount of force before it breaks. So we take one of the parts, we test it by putting the weight on it, and we add weight until it breaks to see if it held enough. Well, that part that we just tested is now destroyed. We can't sell it. If we test every part, you can see where I'm going here, there's nothing left to sell. So you have to figure out how many parts do you have to test, or how often do you have to test parts to make sure they're coming out well, or to at least be reasonably assured that they're coming out well. These samples need to be done in what we call a representative sample. All that means is the results of the sample are really, really close to what the results of the whole population would be. Because of that, we have to be careful on our sampling technique. One, we need to make sure the sample is large enough. If I want to know who's going to win the next presidential election, and I just call up 5 people and ask them who they're going to vote for, and 4 out of the 5 say they're going to vote for candidate A, I can't say 80% of the people are going to vote for candidate A. It's just too small of a sample. So I have to make sure it's large enough. And second, I have to make sure it is random. Now, there's a whole long spiel. I could probably go on for 25 minutes on random and different types of random and all that. We're not going to do that. Random just means there isn't anything that biases the sample, or no predictable bias. But what on earth does that mean? Well, let's say that I want to know if you are in favor of money, increasing funding for high schools. If I go stand outside a high school and survey adults coming in and out of the building, they're strongly in favor of increasing funding for high schools. Big surprise. I can't do anything like that that'll predictably bias my results. I have to do a cross-section of the population. Some people that have kids in school, some people that kids are old enough they're out of school, people that don't have kids at all, all sorts of different people, so that we get a good representation of the whole population. I'm not going to get into that any further, but it's probably the most important part of statistics, because if you don't do that well, all of the data analysis and data organization that we're going to talk about for the next 2 weeks is completely and totally useless, because the data you have is useless. Doesn't matter how well you analyze it or organize it. If you don't have good data, not much you're going to do with it. So anyway, let's start looking at how are we going to organize this data. So let's start out with we're going to look at some categorical data first. And let's say we did a survey to see what people's favorite colors were, and we give them a choice of red, blue, and green. And we just make a list. So here's a list of the results. Red, blue, or green, favorite color. This list is relatively small, but even it is big enough that it's deceptive. Depending on where you look in this list, if you're just trying to look at it and get an impression, the human eye, the human mind can only process between 7 and 13 items at once. So when we're looking at this, we're only seeing between 7 and 13 items at once. So if I'm looking over here, I'm literally only seeing about that much. Well, if I'm looking there, I see 4 reds right together. I'm going to think, hey, red looks like it's going to be the predominant color. Unless I'm looking over here, and I see a whole bunch of greens there. So my mind is going to automatically think green's going to be the predominant color. Too many people make that assumption of, I can just look at a set of data and I can pick out really quickly which one's the most common. It's not so. So what we can do, one of the things we can do is we can organize our data into a frequency table. What a frequency table does for categorical data, it's pretty easy. We have our category here, in this case, the favorite color, and we'll list them out. Red, blue, and green. And then we're going to find the frequency. Now I left a little space here because I like to add in a column here that I use for tallying. This is not really part of the table. I just put it in there to create the table. If I were doing this as a presentation to someone, that column would come out. It's a working column. But if I look up here, I've got red. So I'll mark off the red, put a tally in the red. Another red, a blue, a green, a red, a blue and a blue, a red, green, 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 a red, green, blue, red, red, blue, red, green, red, blue, green, green, red, green, and blue. So now I can see I have 10 red, 7 blue, 9 green. Fairly quick little thing. Again, my finished table, I'd take that tally column out and it'd look just like this with the color and the frequency. So now I can look at my table and I can look at the numbers and see, hey, red is the most common color, most commonly chosen one. There's some other things we can do. We can look at what's called percent or relative frequency. To find the relative frequency, we find the total. There's 26 total responses here, or results that we've got organized. And we just find what percentage or what proportion of the whole works that is. So 10 divided by 26 is 0.385, or 38.5% if you wanted to list it as a percent of the total. What's that? Either way is fine. Technically, if they ask for relative frequency, it should be a decimal. If they ask percent frequency, it should be a percent. I would accept it either way. My math lab may get picky. So 7 out of 26, 7 divided by 26, you get 0.269. And then the 9 out of 26, 0.346. Those better add up to really close to 1.0, or if they're percents, 100%. They may not add up exactly because we did do some rounding here because we rounded off to 3 digits, 3 decimal places. So if it's like 99.9 or 100.1, it's not a big deal. But they should be really close to 1 or 100. That's pretty much it for organizing our data for categorical data. Just write in the categories and you put in the groups. Now from there, of course, we can organize it even further for quick reference. We can put it into graphs. We'll talk about graphs in a little bit. Let's look at organizing numerical data. So if we need to organize numerical data, well, there's 2 different types of numerical data. We have discrete or continuous. Let's start looking at discrete. And let's look at the number of classes a student has. And of course, if you have 0 classes, you're not a student, so there's no need for 0. And let's say we don't have anybody that took more than 6 classes. And again, we would have a list of data up here with the numbers of classes a student's taking, 1, 2, 3, 4, 5, or 6. And we would go through and probably tally them off. Let's just say that we get a frequency of 6. I'm going to do this. 11, 18, 39. Okay, where am I at? 18 and 8. So there's our frequency table. And again, I skipped a lot of steps. You'd have that list of classes. You know, some that had 3, 4, 1, 5, 2. You'd have to count them up to figure out what the actual frequency of each of those is. If you ever understand how to do that, just go through and count them. Okay. I didn't want to waste time making a list and counting them up. So now that we have them organized, just like before, we could make a relative frequency. First step to finding the relative frequency is to do what? Total. What's our total here? What, 17, 35, 74, 82, 92, 100. Good, because that's what I was shooting for. So now this is 6 divided by 100, 0.06. 11 divided by 100, or 0.11, 0.18, 0.39, 0.18, and 0.08. And yes, it does add up to 1.00. There's our relative frequency. So you can see discrete data is not a lot more difficult than our continuous data. Now there may be such things where we can't list out all the possibilities here, even for discrete data. So you might list, might put them in groups, like 1 to 3, and 4 to 6, and 7 to 9, and like that, and so on. So you might end up having to group them together. If you can say anywhere from 1 to 12 classes, you're not going to list out 12 different categories. You might group them together. Well, if we have a continuous numerical variable, well, then it is generally necessary to group them together. If we're looking at surveying the height of people, now I'm not going to make a very big list here, but let's say we have 72.4 inches. And I'm going to leave the inches off from here on out. 68.7, 70.9, 71.3, 67.8, 65.2, 69.1, 71.1, 70.4, and 63.9. Now again, there's only 10 numbers here, but you get the point. To make our frequency table now, we need to find our classes or our ranges that we're going to put things in. Those ranges have to start out small enough that they include the smallest number. They have to be large enough to include the largest number, and they have to be all the same size. So the smallest number up here is 63.9. The largest is 72.4. So it has to go from 63.9 to 72.4. So that means we have to cover how much here? 8.5 units. Now from there, we need to also know how many classes we want. Let's say we want to divide this into 3 groups. So what we would do is we're going to divide this number by 3. 8.5 divided by 3 is 2.833. So that means is we have to have at least 2.833 between the smallest and largest number in each group. So we're going to round that up. We're going to go 2.9 inches is going to be our size. Well, maybe we would even round it up to 3. Let's round it up to 3. Let's make it easy on ourselves. So round it up to 3. So we're going to start out at or just below our smallest number here. I'm actually going to do 63.8. So if we're going up 3, the next one will start at 66.8. And then 69.8. Which means this range is going to end at 66.7. Where did I get 66.7? Has to be just smaller than this one. So if we're measuring to the 1/10 of an inch, that's adequate. This one's going to go up to 69.7. Good. And this one will be 72.7. Did we get big enough? Yeah, 72.4 is all the bigger we had to go. So then that's our ranges. That's our heights. We're going to put our frequency here. Let's see, between 63 and 67, we've got 67.7. So 1, 2, there's 2 in there. 66 to 69.7. 66.8, 69.7. 1, 2, 3, and 69.8. And above 1, 2, 3, 4, 5. Did I count those right? I think so. There we go. Now we can do relative frequency there. There's also something called cumulative frequency that I don't use a lot, but you'll see it in some of the readings. I'll let you pick up on that. If you have questions, we'll look at it more next week. So once we've organized this data in frequency tables, we can make it a little more visual. In the frequency table, it makes it easier to see, but not necessarily really quick to reference. All the tables we made had only 3 or 4 different groups here. What if we had a lot of data? We might have 20 different groups here and still have a large frequency in each. So that's a lot to look through. Even to pick out which one is the largest frequency is tough to do if you have that many categories in your table, that many groups in your table. So we want to go on and organize these into graphs. That's a visual representation. It's usually the advantage, of course. It is very quick to find certain features. You know, larger, smaller, so on. Like which one is the largest frequency? Which one's the smallest frequency? Is A smaller than B, or is M bigger than F, or whatever? So you can compare sizes really quickly between 2 groups. Weakness with a graph, though, is can't really get exact numbers. Especially if you have really large numbers, you're just taking a guess, basically, at what that number is. You're not going to get exact. You can compare rough numbers quickly, but you can't get exact values. So some types of graphs we're going to look at. There's what we call a bar graph. A bar graph applies to our categorical data. So let's say we have our favorite colors listed again. Red, blue, and green, and a frequency. So 10 red, 7 blue, 9 green. A bar graph is just going to have the different classes listed either on the bottom or the side. I'm going to list them on bottom. And some sort of number scale on the other axis. In this case, since my colors are listed on bottom, my number scale goes up the side, and it has to go to at least the largest number. So this one goes to 10. Since it only goes to 10, I can probably just number by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So red goes up 10. Blue goes up 7. Green goes up to 9. So here I can very quickly pick out. Most popular color is red, least popular is blue. Green is somewhere in between towards the top end. If I am using continuous numerical data, a bar graph has a special name. It gets called a histogram. For example, if I was doing the heights, I don't remember the category, so I'm just going to put them down here. Just do 63.8 to 66.7, 66.8 to 69.7, 69.8 to 72.7. So those are my categories. And I didn't have more than 5 in each. So again, I can number by ones. 63.8 only had 2 in that group, 3 in the next group, and 5 in the next. So the big difference you should see on a histogram, one, these are number ranges down here instead of just, identifying some sort of a category. 2, a little more subtle, the bars are tight together on a histogram. Why is that? Well, because there's a logical transition from 66.7 to 66.8. They're next to each other. They should be tight together. They flow together. Same from 69.7 to 69.8. They flow together. So it makes sense that the bars on the histogram flow together. There is no logical connection between red and blue, so it wouldn't make sense for those to touch. Yes, sir?
It has nothing to do with going gradually up or anything like
Nope. It could be, this one could be the largest one. Sure. The reason they touch is because there's an actual connection. The numbers are physically next to each other. Where these, I could put red, blue, and green in any order, and it still makes sense. There's no logical order, no connection between them, nothing like that. Other types of graphs we might have. We might use a circle graph. A circle graph is more commonly used for categorical data.
So there's another name for that, pie chart.
A pie chart is also one of the words that's used for it. In that circle graph or pie chart, let's look at our colors again. Oops. I don't know where the SGL went. Red, blue, and green. I'm going to make up new frequencies. In fact, what I'm going to use a relative frequency here. Because when we go into the pie chart, what we generally are graphing, in fact, what we're usually graphing on the pie chart is not relative frequency, but percent frequency. I can't write tonight. We'll try that again. Percent frequency. There we go. And let's just say we did this and we came up with 38% for the red, 29% for the blue, 33% for the green. So now we go to graph this. In the old days, we would have found there's 360 degrees in a circle. 33% of 360 is like 119 degrees. You'd bring out your protractor, you'd measure it out. Well, now if we want a graph to be that exact, we have computer software that's going to make it perfect for us. So for our purposes, all I care about is some basic benchmarks. Half a circle is what percent? 50%. Quarter circle is 25%. So looking at these, we have blue that's 29%. That's just more than 25%. So that's probably our blue about like that. That's close enough for the blue. 33% is about a third of a circle. So I might do something like that. That is the green. And the 38%, the red is that. Close enough. These numbers are all pretty close to each other, between 29 and 38, so it's really hard to draw them, estimating and get a significant difference between them, but that's relatively close. Another type of graph we're going to show, what the pie chart or circle graph and the bar graph and histogram, they all show a snapshot or a moment in time. Sometimes we want something called a time series data. And what that does is, rather than looking at different choices, they look at a certain value over time. Excuse me. For example, we might look at the cost of books. We might do 1995, 2000, 2005, 2010. Why would I not put 2015 on there? Oh, we just started it. We don't know yet. Now here, because the cost of books can get up into the $600-700 a semester, I'm not going to label it by ones. I'm going to label it by 50, so I have reasonable size markings over here. And we're going off average cost of books. So there's some programs that don't have textbooks at all, so that average is not going to be in that $500 or $600 range. It's going to be much lower. Let's say that for 1995, the average was just under $150 a semester. In 2000, it had jumped to about $190 a semester. 2005, it jumped to about $260, and in 2010, it was at about $270. So by looking at this graph, we can pick out one thing rather quickly. The period over which the price rose the fastest is right there, from 2000 to 2005, because that's where the line is the steepest. The other thing we would be able to pick out quickly, if it ever happened, but it doesn't in this case, is if the price ever went down. We'd see the line going down, so you could tell rather quickly there's a spot where the price dropped, or that value that we're tracking got smaller over that period of time. Again, if I wanted to know the exact average of what students spent on book in 1995, trace this over. I know it's a little bit below 150, but there's no way I can get an exact number. I cannot look at this graph and say it's $146.38, because the graph isn't designed to be that. It's designed to be approximate comparison. Okay, we're 5 minutes early, but that would be a good time to take our break right there, so let's do that.